Okay, so in this video we're going to be looking at free fall on Earth, the acceleration due to free fall, displacements and speeds as you are in free fall, and comparing it to a real life object just to put it into perspective. Acceleration due to gravity on Earth is 9.8 meters per second squared. It does vary slightly with geographical locations, but we're just going to use this as the standard. What does 9.8 meters per second squared actually mean? It means you will gain 9.8 meters per second of speed or velocity for every second that you are in free fall. I've got two kinematic equations here. This one will be determining the velocity or the speed of the object for every second of free fall. And if we're dropping it from rest, that v1 is going to be a 0. And we also have a kinematic equation for displacement. And again, because we're dropping it from rest, so the first term is also going to be a 0. So I've already gone ahead and done the calculation using times from 0 seconds up to 10 seconds for the velocity of the object and for the displacement. And here's the chart. So this chart shows the increasing speed or velocity without air resistance. So at the end of 10 seconds, it will be going 98 meters per second. Here's our chart of displacements, and again without air resistance, at 10 seconds it will have traveled 490 meters. And as a graph, this is what it looks like. Blue line is showing the linear increase in velocity, and the red parabola is showing the exponential increase in displacement. So these were generated using a spreadsheet. We can also make a graph using just Google Chrome. So what I've done is put the equations in here. So this is the one for speed. Y equals 9.8 times x. X is going to be our time. And for displacement, it's 1/2 9.8 x squared. And here's our graph. Now obviously we're not going to be looking at times that go into the negatives. So I can move my graph over like this, and now we can actually track points. So we can track the points for speeds at various times. And by using this drop down, we can actually figure out the exact displacement at specific times. So now let's put this into perspective. How far does it fall and how fast is it going at each time interval? So for the first analogy, I'm using a football field stacked together. Obviously, you'd have to have the football fields vertically. So here's our start position. After 1 second, you've gone 4.9 meters. Here's your speed. 2 seconds, you've gone 19.6 meters. 3 seconds, 4, 5, all the way down to 6. So at the end of 6 seconds of free fall, you are traveling at 58.8 meters per second, and you've traveled a total of 176.4 meters. Now, in order to show the full 10 seconds, I'm using a different analogy. And that is the CN Tower, which is in Toronto, Canada. It has a height of 555 meters. Top of the tower to the base of the tower is 555 meters. So the 0 point is actually the very tip of the tower. In the first second, you've fallen about 5 meters and you're going 9.8 meters per second. So it's not much of a drop at all. And then we can obviously see the linear increase in speed. You're getting faster by 9.8 meters per second every second. But the distances that you've fallen is the exponential. So you'll notice by the spacing of the lines that it is getting substantially larger for each second of free fall. So if you were in free fall for 10 seconds, you've fallen a total of 490 meters, and you'll be going 98 meters per second. Now the ground is only 65 meters away from that. So if you're traveling 98 meters per second and you're 65 meters above the ground, or the object is 65 meters above the ground, it will very quickly make impact.